Good afternoon, everyone. Welcome to the Transoft booth. Thanks for joining us. The Transoft is a company with 30 years of experience, about 180 staff across 14 offices with a global presence. My name is Sandovan. I'm Senior Product Manager here at Transoft Solutions, the safety division. I've been with Transoft and formerly Briss Synergies for 5 years, and I've been working to bring technology to be accessible for transportation planners for over a decade. Today I'll be talking about the applications of big data in safety analysis. This is an ITE tech brief that was initiated as by the ITE Executive Safety Council to prime transportation professionals with knowledge about safety using big data. An important quote in it: as the availability of big data becomes ubiquitous, it becomes difficult for transportation professionals to discern which data sets are most useful for evaluating safety performance. So I and Transoft had a hand in working on this document. We contributed, but it does represent many other vendors as well and transportation consultants. Today I'll share a brief overview of the document without spoiling all the secrets, so you can consult for yourself, and provide some supplementary material. So just a bit of background. So the proactive safety analysis methodology, it's a type of safety analysis that's used when crash data is insufficient or is lacking. So we typically have over here in our hierarchy of safety events, we've got our crashes, which are great when you have them, but there's often missing information. So the big data can come in and analyze a lot of the safety behavior that exists at the lower end of the pyramid. We're talking about benign behavior that goes on every day but still exposes people to risks, incidents that are not detected, that are not reported, etc. So the document covers a few topics. First, it starts with the definition and review of major technologies and data sources using big data. Does a general review of case studies volunteered by submission for IT by community members, a review of analysis of the methodology and applications used, and insights related to the interpretation of information from these big data sources. And finally, it concludes with a needs identification. So the details aren't overly technical, but they're at least enough to understand how the technology is used in the field and in practice by practitioners amongst our community. So we looked at several primary sources of data. There are many of them out there. We considered implementing as many as possible, but ultimately we decided on these 4 sources of big data. We've got excessive speeding and aggressive acceleration and deceleration. We've got recorded violation events, we've got post-encroachment time, and time to collision. And these were all represented in the case studies that were included in the report. And so we have a handy table here to identify some of the benefits and challenges in using each of these methodologies. They're not all perfect. Some are better used in some cases versus others. So for salient facts, the application of excessive speeding is for identification of aggressive and evasive driver behavior. And this source can typically come from specialized vehicle instrumentation for network coverage, but it could also be using video and LiDAR data or even more basic traffic counting technologies to get point-based information. Next, we've got recorded violation events, which identifies illegal driving behavior, violations similar to automated enforcement. This is primarily based on video and LiDAR. Post-encroachment, which identifies collisions or potential collisions involving 2 road users, also primarily using video and LiDAR. And then finally, time to collision, very similar to PET, but augmented in those situations where PET lacks. So generally speaking, PET is applicable sort of universally in all types of infrastructure. However, it has challenges in certain scenarios, whereas time to collision is really a universal indicator of potential for danger. So in terms of maturity in the technology, you kind of see some themes. So post-encroachment time is a more simplified approach, but it does, like I mentioned, it lacks details in certain scenarios, whereas time to collision can cover that. And I'll explain in a supplemental material what I mean by that in a second. For the recorded violation events, obviously it's capturing violations as defined by the legal process. The limitation there is that you're limited to whatever the legal process defined as a violation or not. So even safety behaviors that are not necessarily codified in legislation may not be captured using this type of information. But otherwise, it's a pretty mature and very accessible approach. So for some supplemental material, these weren't included in the report, but I did want to include them in my presentation just for additional context. So obviously here we have a conflict, a very typical example, although this is an extreme case of a very obvious near miss. Most conflicts are actually a little bit more benign than that, even though they do contribute still to some safety prediction. And on the right here, we have an example of patterns that we observe when we look at the data in more aggregate. In this case, we're looking at speed behavior. So we can see some patterns. The lighter colors are higher speeds. We can see some patterns of road users accelerating as they exit the roundabout, a little bit here, but especially on this approach and this movement, a little bit of acceleration leaving the roundabout. We see here very high speeds at the merge zone between these two movements, whereas over on the bottom here, slightly lower speeds. So that's an interesting pattern that we can discern by looking at this type of big data. So I did mention TTC, and I did want to explain how it does differentiate from PET a little bit. So whereas PET measures the actual observed behavior, and maybe I'll just explain this graph a little bit, getting back a little bit to transportation theory, we've got time-space diagrams. So we've got time on the x-axis and distance on the y-axis. And here we have in A, we have car A that's traveling a certain distance over time, and we have a stationary car B here that represents an obstacle for car A. So car A is on a trajectory, literally a straight line into car B. And so when we're using PET, what we're really doing is we're finding the difference, we're finding this time, which corresponds to the margin of safety that the road users have. Whereas what time to collision is doing actually is well before we observe this, we extrapolate the potential and future positions of a road user constantly and up to date, continuously. And that tells us whether we have a conflicting point or not. So obviously time to collision is a little more complex because it involves extrapolation of movement and understanding road user behavior modeled directly at the site, but it's able to cover situations that make a little bit more sense, especially in rear ends. For example, when we have car following in a typical time-space diagram, we might see multiple car trajectories. So if we're doing PET constantly between these cars, we're going to get a whole bunch of false positives because the car moving ahead of the road user, the car ahead of the first road user is constantly moving ahead and out of the way of the previous road user. So only TTC can capture that kind of behavior. All right, so getting back to the report to review a synthesis of the case studies. There was a call for case studies posted to the ITE community forum in the spring of 2022. And we had 6 case studies respondents from the US, different municipalities each, and 1 case study in India representing data from different vendors and analysis from different engineering firms. Typical data collection was a week to 2 months for almost 90 sites. And in one case, we had a full coverage over the entire network. Technologies included stationary video, drone video, LiDAR, and connected vehicle data. So in terms of application, in terms of the road safety management process that's typically used in road safety engineering, it's codified by the Highway Safety Manual. The projects were mostly targeting on network screening and diagnosis, which is to be expected. Although I was expecting to see actually more studies in the safety effectiveness evaluation. In fact, that's where I typically start projects, to build up a data set for network screening. Anyway, you can read that more in the tech brief. And there was a section on big data interpretation. It's important to understand what the data means and how it relates to safety. There were 2 passages I think that stood out that illustrate the point. So one passage mentioned a simple count of near-miss events with the same PET threshold may be used to compare the frequency of near-miss events at different locations. So in other words, without conversion factors and without necessarily predictive modeling, this data is still useful in comparative analysis. And the second point, since near-miss events are not dependent on rare crash occurrences, near-miss analysis may be readily applied to before and after studies. It's great for pilot projects. Finally, the document had a needs identification. So the needs for future work and clarification in the documentation and standards included identifying the variability of PET by locality and for traffic congestion, identifying the impact of big data in safety analysis on crash modification factors. That kind of relates to the road safety management process I identified earlier. So, after the diagnosis, moving into countermeasure selection and evaluation. And finally, integration of big data with safety and smart cities. So I'm finally leaving you a link to the document. I highly suggest you consult it. And with that, I thank you very much.